Bismillahirrahmanirrahim. Assalamu alaikum. So we will solve chapter 20, presentation problems. But before, there are two problems that I would like to solve from chapter 19. So the first problem is this one. It reads, an ideal monoatomic gas at initial temperature T1 and initial volume of 2 meter cube is expanded adiabatically to a volume of 4 meter cube. So let me write the data of the problem. So first, I give you an initial state. Let me write it as state number 1. So I give you the temperature, T1. I did not specify it, but it's like a given. And I gave you V1. What is V1? 2 meter cube. I did not talk about the pressure, okay? But I can just add it for sake of completeness. So this is state 1. Then I said this is expanded adiabatically. So I have an adiabatic expansion. So adiabatic expansion. And I go to state 2. Now state 2, what is the temperature? It will be T2. I don't know it, but I can know it. Okay? And I know that for a fact it will be smaller than T1 because it's an adiabatic expansion. Of course, the temperature will decrease. Now, what is the volume 2? It's given 4 meter cube. And what is the pressure 2? It's not given, of course. If I want, I can get it. Then, now I'm here. It's expanded isothermally to a volume of 10 meter cube. So I have isothermal expansion to state number 3. Now state number 3, what is temperature number 3? It's an isothermal expansion. So T3 is equal to T1. T2, okay? Because I'm expanding from state 2. And this will be smaller than T1, and we will find it. What is the volume now? Volume 3 is 10 meter cube. And pressure 3, nothing is said about the pressures, so yeah, I'm just writing it for the sake of completeness. Then finally, it's compressed adiabatically. So this is a key word here, back to T1. So I have adiabatic compression. So T4, so this is my state number 4, the final state. T4 is equal to what? T1. V4, I don't know. And by the way, that's a question, because the question is what is the final volume? What is V4? And P4, I don't know, okay? So you see here, I did not talk about the pressure at any point. So I can forget about the pressures. I will just focus on the temperature and volume. First, I have an adiabatic expansion from 1 to 2. Second, I have an isothermal expansion from 2 to 3. Then I have an adiabatic compression from 3 to 4. Now let's solve it. So, and then the question is, what is V4? What is the final volume? First, let me exploit this. I have an adiabatic expansion. Adiabatic, of course, I know that temperature multiplied by V to the power gamma minus 1 is a constant. Okay, so that means T1, V1 to the power gamma minus 1 will be equal to T2, V2 gamma to the power minus 1. Okay, because it's an adiabatic process. Remember, adiabatic process, of course, the V to the power gamma minus 1 is a constant, but also PV to the power gamma is a constant. Here, I did not give you the pressures, so this is what I will be using. Okay, good. So what is T2? Easy. T2 will be just T1, V1 divided by V2 to the power gamma minus 1. In other words, it will be equal to T1. V1 divided by V2 is just 2 divided by 4. So this will give me 1/2. Now, what is gamma? It's a monoatomic ideal gas. As you know, for a monoatomic ideal gas, gamma is just 5 divided by 3, which is just Cp divided by Cp. So gamma minus 1 will give you to the power 2/3 here. So I know temperature T2. And this indeed is smaller than T1 because of this factor. Good. So now I have an isothermal expansion, right? From state 2 to state 3. Now, since I have an isothermal expansion, as I said, T3 is equal to T2. So this basically will give me T3. Okay. Good. Now, what do I have here? And I have an adiabatic compression. So an adiabatic compression, I still have TV to the power gamma minus 1 is a constant, but now I will apply it between 3 and 4. So T3 V3 to the power gamma minus 1 will be equal to T4 V4 to the power gamma minus 1. But you remember T4 is equal to T1. So let me exploit this. Of course, I will have T3, and T3 will be T1 1/2 to the power 2/3. Okay. Multiply by V3. V3 is 10 to the power 2/3. And this is equal to T4, and T4 is equal to T1. And I will multiply by V4 to the power 2/3. Okay. You see the T1 was a parameter, it simplifies, and I have my V4. Okay. So if I have V4 here, of course, all of them have the same power. So I take everything and I multiply by 3/2. I take to the power 3/2. So basically I will have that V4 is just equal to 1/2 times 10, which gives me 5 meter cube. Okay. So this 5 meter cube is my answer. Okay. And this is a good problem. That's why I wanted to solve it for you to see. If I remember, when we gave it as an exam, only 30 to 35% of students, they got it correctly. Okay. Good. Is it clear? Okay. Now let me go to the next problem now. So the next problem is this one. So it says that a sample of an ideal gas undergoes this cycle shown in this figure, as you can see. Okay. So it goes from A to B, constant volume process, B to C, and it's an isothermal process. So this P is a constant, so isothermal process. Then C to A, constant pressure process. Okay. So I have a PV diagram. P is in atmosphere. Of course, you put it in Pascal. V is in liter. Of course, you put it in meter cube. The question is, what is the net work done in one cycle? So we want to calculate the net work for a cycle. So how can we solve the problem? So let's use, for instance, net work for the cycle will be work from A to B plus work from B to C plus work from C to A. Okay. This is the work that I want to calculate. Okay. Now, what is the work from A to B? Well, as you know, work is integral of PdV between the initial and final state. So A to B is an isovolumetric process or isochoric process, constant volume process. So work from A to B is equal to 0. Now, what is the work from B to C? And then it's an isotherm. Right? So work from B to C, as we showed in class, is an RT logarithm V final, and V final is VC here, divided by V initial, which is VB. Okay. But the problem is I don't know T. I can get it easily because it's an ideal gas. So I know that PV is equal to nRT, and T is a constant. So this is a constant. So nRT here is just PB, because it's on VB, which is equal to PC VC, which is equal to nRT. Okay. So this nRT here, I can replace it by PB VB, which is the same as PC VC because it's the same isotherm. Okay, isotherm, don't forget it. B to C is an isotherm. So work PC, I just replace nRT by PB VB logarithm, or ln, natural log of VC, V final divided by V initial, which is VB. So let's calculate it. PB, I know it, it's 3 atmospheres, so 3, 1.01, 10 to the power 5 Pascal. VB, I multiply by, so I have 5 liters, so 5, 10 to the power minus 3 meter cube, right? So this will give it to me in joule, and I will have ln of VC, which is 15, divided by VB, which is 5. So this will give me the work along the path BC. Okay, and it's a positive work, okay, because it's an expansion. So you calculate this, it will give you a number. Now, what is work CA? Well, work CA happens at constant pressure. So it will be just P. Okay. So it will be P. What is P? Of course, it will be PA, which is the same as PC. What is VV? It will be VA minus VC. Now it will be 1 atmosphere. So basically 1.01, 10 to the power 5 Pascal. Now VA is known, it's just 5 minus VC, which is 15. But don't forget, I have to put it in meter cube. 10 to the power minus 3 meter cube. And then I can calculate it easily. Okay. Now when I take this one, PBC plus VCA, I add them, I will get the right answer, which is just this answer here. Okay, good. Now, if I ask you, what is the heat? What is the net heat exchange during one cycle? So basically what you use Q net heat exchange during one cycle. What will you do? It's a cycle, of course, you have change in internal energy is 0. Okay, internal energy is a state function. So along the cycle, a full cycle, the change in internal energy is 0. So the change in temperature is 0. First law of thermodynamics, this will be equal to Q minus W. Okay, that means that the Q net will be just equal to the W. Yeah, so I will have the same answer, which is this answer.